Hello and welcome. My name is John Horvath, and this presentation is about the Whitehouse Station, New Jersey earthquake of April 5th, 2024, and its place in the seismic history of the New York City metropolitan region. I should mention that at the time I'm making this recording, this earthquake occurred less than 2 weeks ago. So this is very recent information. And I think it has tremendous time value, which is why I decided to produce this presentation. I've divided this presentation into segments, as I usually do. This is to organize the material in a rational manner, as well as to facilitate it for those of you who are viewing this presentation. I've had people tell me that they often like to watch one segment at a time as they have available time. So let me start off with some introductory comments to kind of set the stage as to why I decided on very short notice to do this presentation after this earthquake occurred. Seismic events of sufficient magnitude to be felt by the general population are they relatively infrequent in New York City and the surrounding metropolitan region. And I say this on a first-hand basis. I was born and raised in New York City and have lived in the suburbs of New York City for my entire life. And I certainly felt this most recent seismic event on April 5th. I happened to be working in my office at the time. So it was obvious to me pretty quickly that we were having a relatively significant seismic event. Even less frequent in the New York City metro region are seismic events of sufficient magnitude to cause physical damage to constructed facilities such as buildings, bridges, and infrastructure, especially underground infrastructure. And this damage can occur through either direct shaking or seismic liquefaction, or, believe it or not, possibly even a tsunami. Any coastal region such as New York City and surrounding area has to think about tsunamis. In any event, because of the relatively infrequent seismic history in this region, regional planning for seismic events has, at least to date, been very spotty at best. And again, I say this on a first-hand basis. All of my professional education has been here in the New York City area, and all of my professional practice, while global in nature at times, has been based here in the New York City area. So I have certainly a first-hand perspective of how earthquakes are viewed in the New York City area. Code requirements for seismic design nowadays only apply to relatively new or rebuilt structures that are fairly substantial, such as bridges and tall buildings. So seismic upgrading of older existing constructed facilities, and I'm thinking here primarily things like single-family residences and underground utility lines, has not in general been done, so these facilities are ill-equipped to withstand a significant earthquake. I think just as importantly, there's been no systematic education of the public at large within the New York City metropolitan region about seismic history, what we call seismicity, seismic potential, and even something as basic as how to react during a seismic event. So there's really no earthquake preparedness at all. I'm sure first responders have gotten some training. I would like to believe have gotten some training in this regard, but certainly the public at large has not. The bottom line is that even when a modest seismic event occurs in the New York City area, it tends to cause substantial alarm and get inordinate press coverage. And my experience has been is that this press coverage invariably includes incomplete and sometimes inaccurate factual information. What you tend to find is that the various TV channels and newspapers, online news sources, they actually tend to repeat the same very few number of facts that have been put out to the public. Well, this was the case on April 5th. As I said, at the time I'm making this presentation, less than 2 weeks ago, April 5th, earlier this year, 2024, when a relatively large, at least for this area, earthquake occurred. As we'll see, it was epicentered in northern New Jersey and was certainly felt throughout the entire region. As I said, because this happened during the day, I happened to be working in my office, second floor of a very typical single-family house that is supported on bedrock. And the sensation I felt was very, very deep rumble. Things on my bookcase shelves started to rattle and tinkle. And very quickly I realized it was an earthquake, and I was surprised at how significant the earthquake was. In the years that I have lived in this house, I've actually experienced several small earthquakes. So earthquakes were not unknown to me personally, but I certainly realized this was certainly the biggest I had experienced to date. So the U.S. Geological Survey relatively quickly officially named this the 2024 4.8 Whitehouse Station, New Jersey earthquake. Although the public was perhaps surprised, seismicity and seismic potential in the New York City metropolitan region in general, and an earthquake of this magnitude in particular, they are not a surprise to geologists and civil engineers who are knowledgeable about this region, at least in recent years. And I do emphasize recent years. As I said, all of my professional education 50 plus years ago was in the New York City area, and I could tell you that during my undergraduate and graduate education in civil engineering, the subject of earthquakes in the New York City area was not discussed at all. It was not something that was thought possible to happen. It was only in the latter decades of the 20th century when geologists, especially those affiliated with the Lamont Doherty Earth Observatory of Columbia University, which is based in Palisades, New York, right across the Hudson River from New York City. These geologists were proactive in educating design professionals in the region about the not insignificant seismicity and seismic potential within the region. As a result, for some years now, regional building codes have required seismic design for certain categories of new or rebuilt structures, and state codes for transportation structures such as bridges have followed suit. Because of this relatively newfound appreciation of seismic potential, when I started my YouTube channel back in 2020, and the first narrated PowerPoint presentation I posted on that channel was about the history, the geotechnical history of the John F. Kennedy International Airport in New York City, at least up to that point in time. I certainly discussed seismic potential in some detail in that presentation. And subsequent presentations that I've posted to my YouTube channel that where the topics relate specifically to the New York City metropolitan region have routinely included a discussion of regional seismicity in general and its particular relevance to site characterization, especially with respect to cyclic or seismic liquefaction. As is now well known to geotechnical engineers, for certain subsurface conditions, seismic liquefaction can be potentially more damaging than direct shaking from an earthquake. The primary purpose of this presentation, as I said, I decided really on short notice after this event occurred that I thought it would be interesting to make a presentation about it. is to revisit the seismicity of the New York City metropolitan region because I had discussed it in my earlier YouTube presentations, and I wanted to see how the 2024 Whitehouse Station, New Jersey earthquake fit into what we currently know about regional seismicity, both in terms of epicenter locations as well as earthquake magnitudes. And a secondary purpose of this presentation is to again discuss the current capabilities for what I call liquefaction screening of coarse-grained soils using results from a piezo-cone or seismic piezo-cone soundings. Given the potential for seismic liquefaction in many parts of the New York City metropolitan region, this relatively recent and still evolving concept of liquefaction screening using cone-penetrometer data was discussed in my most recent YouTube presentation that I made earlier this year, back in February 2024, that was a follow-up about Kennedy Airport and site characterization at Kennedy Airport. And I thought it warranted some discussion of liquefaction screening in view of this recent seismic event in New Jersey. Well, that brings us to the next presentation segment. I want to talk about the seismic events of March and April 2024 in some detail. The Whitehouse Station, New Jersey earthquake occurred on Friday, April 5th of this year, 2024, at 10:23 in the morning. So because it happened on a normal workday weekday during daytime hours, certainly it was felt by a maximum number of people, I think. The epicenter was reported to be approximately 65 kilometers, 40 miles west-southwest of Midtown Manhattan in New York City. If you look at this map, here's New York City, here's Manhattan, and here is the epicenter of the main shock, as it is called. The official magnitude was reported to be 4.8. This is using the regional moment magnitude scale with a focal depth of 4.7 kilometers or almost 3 miles. Earthquakes that occur in the New York City metropolitan region tend to be quite shallow, no more than a few kilometers below the ground surface. As a result of the magnitude and the relative proximity to New York City, motion, which would be a combination of ground motion with structure amplification as appropriate, was widely felt throughout the New York City metropolitan region. I could tell you that within a minute of the earthquake being felt in the area, there were people already reporting online, did we just have an earthquake? Did we just have an earthquake? So here's a location of the main shock on a larger scale drawing. And here's the place name of Whitehouse Station that gave its name to this event. Why the U.S. Geological Survey chose this place name instead of other place names that are perhaps closer by, that I don't know. The main shock was followed by, believe it or not, almost 50 aftershocks that were clustered around the epicenter of the main event. These aftershocks continued for almost a week until April 11th and included one on April 5th, the same day as the main shock, that had a magnitude of 3.8, slightly deeper focal depth, 7.1 kilometers, a little bit more than 4 miles. And I will tell you that this aftershock was also widely felt throughout the region. It happened just a few hours after the main shock. So as I had indicated earlier, I decided pretty quickly, kind of spur of the moment, thought it'd be interesting to do a presentation to see how this event fit into the scheme of things. But I kept waiting day after day after day until the aftershocks ended. I was quite surprised to see that many aftershocks. So here's the same large-scale map showing the main shock. All of these yellow dots are aftershocks, and this was the largest aftershock. As I said, occurred just a few hours after the main shock. What does not seem to have been mentioned in the press, and as I said, this got a tremendous amount of press coverage locally because it was such a relatively rare occurrence, is that there had been a relatively small earthquake, magnitude 2.2, on March 14th of this year, so just about 3 weeks prior to the main shock on April 5th. And the epicenter of this earlier event, which I think can be reasonably interpreted to have been a foreshock, was approximately 2.5 kilometers to the south of the main shock, with a focal depth of 9 kilometers, so about 5.5 miles. So here's the location of the foreshock, and you see that it really fits within the cluster of aftershocks, and that's why I think it can reasonably be taken to be a foreshock, even though it was 3 weeks prior to the main event of April 5th. Yes, I know foreshocks are usually occur closer space and time to a main shock, but I think in this case it's reasonable to call this a foreshock for this event. In any event, the seismograms that I showed on the opening slide of this presentation were recorded at the Lamont Doherty Earth Observatory, where they have station PAL of the Lamont Doherty Seismograph Network. And Lamont Doherty is located about 80 kilometers from the epicenter of the main shock of April 5th. So here again is a map of the New York City metropolitan region, the location of the main shock, and here is the location of Lamont Doherty Earth Observatory, sitting on top of the Palisades, in Palisades, New York, just over the state line from New Jersey, and you see it is across the Hudson River from Westchester County in New York. And PAL is just the official name of the seismograph station at Lamont Doherty. Now, based on the measured time delays of arrival of the P and S waves at station PAL, 14 and 24 seconds respectively, I calculated the average wave speeds between the epicenter of the main shock and Lamont Doherty seismograph as approximately 5,700 meters per second for the P wave and 3,300 meters per second for the S wave. And from what I can see online, these are within the ranges of values that can be found in various online sources. So, having talked about the events of April 5th and the foreshock and the aftershocks, let's talk about how this event fits into the overall regional seismicity of the New York City metropolitan region. In recent decades, geologists have traced the seismicity or seismic history of the New York City metropolitan region back to the 17th century European colonial era. A lot of this work has been done by researchers at Lamont Doherty. The historical record, which is largely based on information recorded at the time of a seismic event, obviously seismographs have only been used in recent decades to record it in an exact scientific sense. So a lot of this is based on the human-felt older events that were documented in the record at the time. The threshold for human sensation of an earthquake is not fixed. It's often stated to be about magnitude 3, although certainly under the right physical circumstances, humans can sense an earthquake typically in the 2-something range. As we know, the ability of humans to sense dynamic motion depends on a lot of factors. For example, if you're lying down horizontally, you're more sensitive to motion than if you're standing or sitting. If you're in a taller building where you may have some structural amplification of the ground motion, you're going to feel it more readily, things like that. In these studies that have been done, the earthquake epicenters could only be estimated very approximately in many cases for understandable reasons, and earthquake magnitudes only estimated using a 2-step procedure, using modern-day correlations between physical damage that was reported at the time, for example, chimneys falling down, things like that. So we have modern-day correlations between descriptive physical damage that was observed and reported at the time and what we call modified Mercalli intensity, which is a qualitative scale of physical damage. And then we can correlate MMI to magnitude, which is a quantitative scale of energy release. As is known, earthquake magnitude, although expressed as a dimensionless number, is really a metric for the estimated amount of energy released during a seismic event. So despite its shortcomings, this curated and synthesized knowledge dating back to the 17th century is very useful, as it is the only single body of technical knowledge that geologists and civil engineers in the New York City metropolitan region can reliably refer to in order to try to come up with seismic design criteria. Note that of even, I think, greater importance than cataloging earthquake magnitudes and epicenters has been a document known pre-existing brittle faults, especially those that are seismogenic, that is, capable of generating an earthquake. The basic reason was stated by Dr. Charles Magurian and his son, Mickey Magurian. It is generally agreed by all geologists and seismologists that abrupt movement on dislocations known as faults produces earthquakes. Thus, pre-existing faults tend to localize new earthquakes. And essentially what they're saying here is what we've known for a long time, and that is an earthquake is basically the release of pent-up energy in the Earth's crust. And earthquakes tend not to cause new cracks, new faults to occur in bedrock. Rather, earthquakes tend to occur along pre-existing brittle faults where we already have a crack, which makes sense. I mean, if you have, bedrock is nominally a true solid, and with any true solid, if you have a defect in that solid, then failure of that solid is more likely to originate at the location of the defect rather than within sound material. And Magurian went on to say that the bedrock of New York City always considered to be solid and impervious to seismic activity, and certainly when I was a student many decades ago, that was always the way it was presented. The bedrock of the New York City region is really cut by a surprisingly number of ductile and brittle faults. Unfortunately, identifying these pre-existing brittle faults in general and those that are seismogenic in particular in the New York City region has always been a challenge, because the experience has shown that faults that originate earthquakes don't always exhibit themselves as a physical crack, what we call a fault trace on the ground surface. You know, this is not like California. If you go out to California, you can physically see the San Andreas Fault on the ground surface. I mean, there is a physical crack that extends all the way up to the ground surface that defines the San Andreas Fault throughout the length of California. The brittle faults we have in the New York City metropolitan region do not always, in fact, in many cases, do not produce a fault trace on the surface. Even in an area where the bedrock outcrops. And this is complicated further where, as Dowers and Sieber noted in their 1991 paper about the 1985 magnitude 4 Ardsley earthquake in Westchester County, just north of New York City, very close to where I live and have my professional office, that in studying this earthquake in detail, they noted that fault traces are, even where bedrock outcrops, are rarely seen. Further complications, many parts of the New York City metropolitan region, the bedrock is covered by relatively thick deposits of sediment soil. So this is going to tend to cover up any fault traces that might exist as well. In any event, this curated and synthesized body of knowledge about seismicity in the New York City metropolitan region, I've discussed it in detail in my earlier presentations dealing with Kennedy Airport. Again, this presentation back in May 2020 was the first one I posted to my YouTube channel. And this follow-up where I focused on site characterization using the cone-penetrometer at Kennedy Airport that I just posted earlier this year, February 2024. In both of these, I discussed the earthquake history in New York City area in detail, primarily from the viewpoint of potential seismic liquefaction at Kennedy Airport, which is a real potential problem. So I'm only going to summarize the body of knowledge here, and I'm going to update it based on the cumulative seismic events of March and April of this year to see how they fit into this pre-existing regional information. I'm sure that in the coming months and years that geologists will be publishing many reports and technical papers and articles about the seismic event in April of this year. But I just wanted to add my thoughts, at least on a preliminary basis, in this presentation. So this is one of my favorite graphics. This is a map that was produced by Sykes et al. And it shows all the earthquakes that they could find between 1677 and 2004 in the New York metropolitan region, and then some. As you could see, they extend down into Pennsylvania. This map covers a very large area. The black lines that you see, these are known brittle faults. Because of the very small scale used here, there are faults in New York City, especially Manhattan Island and the Bronx, that are not shown. I'm going to show those in a minute. And then you see here all the different symbols, different shape, size, color, etc., or for the seismic events that they could find. Now, I want to point out two events in particular that are shown with open circles. Here's one from 1737 and another one from 1783. I bring these to attention because these were believed to have been very significant events, as we'll see, among the largest that have been recorded in the New York City metropolitan region going back to the 17th century. Yet their epicenters are very, very poorly known. In the Sykes et al. Publication, they mention that these epicenters could be very different by quite some number of kilometers or miles. So these are only very approximate locations. These are more detailed drawings for Manhattan Island and the Bronx in New York City. The largest known brittle fault, and there are several in Manhattan, is the so-called Manhattanville Fault, also called the 125th Street Fault. This has been associated with several minor events that have occurred in recent decades, and one most recently at the very beginning of this year that was epicentered in Woodside, Queens, seems to have been associated with an extrapolation of the Manhattanville Fault into the borough of Queens in New York City. And as typical, this is a relatively shallow event, just a few kilometers. In the Bronx, the most significant brittle fault is variously known as the Mosholu Fault or Mosholu Parkway Fault or Van Cortlandt Park Fault. Different names have been used in different publications. Mogurian, in his publications, talks about the East 204th Street bulge, as he calls it, that appears to be associated with this fault. There are some interesting things going on in the New York Botanical Garden, which is situated here. If you're interested in geology of the region, you should find some of the publications, including one that just came out within recent days, April of this year, by Dr. Mogurian and his son, Mickey Mogurian, talking about the geology of the New York Botanical Garden. Some interesting thoughts about why the Bronx River shifted its course at some time in the geologic past. But there are other faults in the Bronx, the Bedford Park Fault, the Fordham Fault. I personally think there's another fault called the Mount Hope Fault. Several years ago, I did a forensic investigation for a structure along the Grand Concourse here in the Bronx, and to my semi-geologic trained eye, I have to think that there's possibly a brittle fault running through this area. It may be an extension of the Dyckman Street Fault that is found in Upper Manhattan. In any event, going back to the graphic from Sykes et al. Here's the location of the Whitehouse Station earthquake of 2024 and all the aftershocks. And it correlates very nicely with the Ramapo Fault. Some publications nowadays call it Ramapo Fault Zone because it appears to be made up of a number of faults. So there is pretty good correlation with a known brittle fault, and the Ramapo Fault is one of the relatively rare faults in the New York City metropolitan region where you can see the fault trace. If you ever go up Interstate 287 through this part just before you reach Rockland County in New York State, you actually can see the fault trace before your very eyes sloping up from the highway. Very dramatic. So the Ramapo Fault, called the Newark Basin Border Fault in some publications, was apparently created during the breakup of the supercontinent of Pangaea that began about 200 or so million years ago. Here is the supercontinent of Pangaea. I'm sure you've seen this graphic in many books. And here's the location of what became the New York City metropolitan region. And you see with Pangaea, this was certainly within the overall supercontinent. Well, what happened, as I said, beginning about 200 million years ago, all of these parts of Pangaea began to spin off in different directions. In particular, there was a split between North America and Africa, basically pulling apart in this direction and forming today's Atlantic Ocean in the process. So during this breakup of Pangaea, as you can imagine, the Earth's crust was stretched and thinned, and this allowed a relatively classic rift valley to form here in what is now the New York City metropolitan area. And the Ramapo Fault is now understood to define the western border of this relatively classic rift valley that is today's Newark Basin. This kind of light yellow covered zone is what we call the Newark Basin. And the Newark Basin is underlain by a sequence of sedimentary rocks. These sedimentary rocks within the Newark Basin have been intruded by a complex series of igneous dikes and sills and lava flows that form very well-known topographic features in this part of New Jersey, because obviously the igneous rocks are much more resistant to weathering than the sedimentary rocks into which they intruded. So this is a nice little geologic profile, a cross-section along Interstate 80, roughly in this direction here. And underlying here, we see the basement rocks, the Earth's crust. So we can imagine that as the Earth's crust was stretched horizontally with the breakup of Pangaea and it thinned out, that we had this rather significant fault zone defining one side that we nowadays call the Ramapo Fault or Newark Border Fault. And into this basin here, sediments were washed, and these sediments were lithified into sedimentary rock. Most of these sedimentary rocks are shale. You will find some sandstones in places, and around the margins what is called fanglomerate, which is a subset of conglomerate, so containing large gravel-sized pieces. So as you can imagine, with sediments washing down into this basin, that the bigger particles will settle out more quickly. These became fanglomerate. A little bit farther on, the sands will settle out, become sandstones, and then the finer grained material becoming clays that lithified into shale. And because the Earth's crust was thinned, we had cracks in the Earth's crust that allowed magma to come up in the form of dikes and sills, and in some cases lava flows on the Earth's surface. The lava flows became the three Watchung Mountains, first, second, and third Watchung Mountains, that very prominent in this region nowadays. And the Palisade Sill, as it's called, very prominent bluffs that you see across from Manhattan Island and Westchester County. And Lamont Doherty is sitting right on top of an exposure of the Palisade Sill. So the Whitehouse Station earthquake was epicentered somewhere along this fault zone here, and you see it was kind of a straight shot to be recorded at the Lamont Doherty PAL recording station here. So as you know, if you've taken geology, these sorts of rift valleys are referred to as Graben, which is the German word for grave, and the higher parts in between are known as horse. So this is a rather classical features that we find in geology. Looking at another graphic, this one was produced by Cormier et al. A few years ago, and it shows all of the recorded events, a much smaller time frame, between 1970 and 2003. And these were events that were recorded by the Lamont-Doherty seismic network. Lamont-Doherty at one time was funded to have a network of seismographs throughout this region. And you see here they call the Ramapo Fault the Newark Basin Border Fault, and you see that as this group of red lines trending across here, and again the Newark Basin, right? So the Ramapo Fault here, the red lines here, the Newark Basin here is the Newark Basin here. Here's the 1985 Ardsley earthquake that I mentioned previously, very close to where my residence and business office located. And you see that at the time that this graphic was prepared, the largest event recorded on the Ramapo Fault was in 1994, an earthquake with a 4.6 magnitude down here near Reading, Pennsylvania. Well, we see that the Whitehouse Station earthquake of this year, magnitude 4.8, actually beats that. So it's kind of interesting to see that at least within this 30-plus year time span of recording earthquakes along the Ramapo Fault, and even if you look here, going back to the 17th century, trying to document recorded earthquakes along the Ramapo Fault, certainly this Whitehouse Station event of April 5th, 2024, is by far, quite by far, the largest seismic event to have occurred along the Ramapo Fault, especially here in the New York City metropolitan region. If you look over here, this Reading event would have been down here. If we look at the focal plane solutions, this is for the main shock of the 2024 Whitehouse Station event. The aftershock was pretty much identical. These are the so-called beach ball diagrams they talk about in seismology. And without getting into the details, essentially what these diagrams show, and you notice that the 2024 beach ball is very similar to these beach balls, as all of these events along the Ramapo Fault are primarily what we call reverse faults or thrust faults. And several of them, including the 2024 event, have a slight strike slip component as well. That's this little piece you see here, here, a little bit, very little bit here, certainly over here. So the 2024 event and several of the earlier events along the Ramapo Fault, these are what we would call oblique faults. Most of the movement was of a reverse or thrust nature, but there was also a strike slip component to it as well. So certainly, I mean, this contrasts, for example, to the main shock of the Ardsley event was a very classic strike slip event. And as I pointed out to you earlier, all of these brittle faults we find in Manhattan and the Bronx, and some of them continue up into Westchester County, these all appear to be strike slip type of faults, brittle faults. Although it was interesting, the aftershock, one of the aftershocks of the Ardsley earthquake was a reverse or thrust type of movement. We look at another historical tabulation. This was done again by the seismologists at Lamont-Doherty. This is a tabulation of the largest earthquakes in the New York City metropolitan region between 1627 and 2001, kind of a similar time frame to what is shown here in the Sykes et al. Paper. And they were organized by Richter magnitude. And I do again want to point out that they noted that several of these events including ones that are fairly significant, like 1737, 1847, 1848. These are very poorly determined in terms of location. Fairly significant or fairly confident about their significant magnitude based on damage reports, but where exactly the epicenters occurred. Again, these are the events with the open red circles we see here and here. A lot of uncertainty as where the epicenter was. It is of interest to note that the largest known event within these time frames was a magnitude of about 5.2, was epicentered here in the Atlantic Ocean, just offshore of New York City. And those of you who have watched my presentations about Kennedy Airport know that I've talked about this event significantly because Kennedy Airport is right here. So the epicenter of this event was very close to Kennedy Airport. And when we're getting into the 5 magnitude range, we're starting to get into events where seismic liquefaction becomes possible under the right conditions. So where does the 2024 Whitehouse Station event fit into the scheme of things? Well, it ranks pretty high, as you could see. All right, so we see that the 4.8 actually on this tabulation of known events in the New York City area, this 4.8 ranks quite high. It's only a bit below. In fact, when it was initially reported, it was tentatively reported as a 5.0. And then very quickly, the USGS scaled it down to 4.8. So, but this ranks quite high in the pecking order of known events in the New York City area. So this was in the scheme of things, although to date there have not been really reports of any significant damage. In the scheme of things, it is quite a significant event. And certainly in terms of what has been seen along the Ramapo Fault, was an extraordinarily significant event. As I said earlier, the largest event by far that we have seen along the Ramapo Fault going back to the 17th century. So I think this the event of April 5th of this year will get a lot of interest from seismologists in terms of very detailed research for a number of reasons. I'll just point out that the Ardsley earthquake of 1985, I remember this was early on a Saturday morning, like about 6 o'clock on a Saturday morning. I remember feeling that earthquake. That was epicentered right about here. That ranked fairly high in the scheme of things, and I'll point out a couple of smaller earthquakes a little bit more than 20 years ago. These were epicentered along the Manhattanville or 125th Street fault of Manhattan. So although these were small events, they were large enough to be felt. And again, one of the reasons why events in the New York City area tend to be felt in the 2-something range is they all tend to have focal depths that are very shallow, no more than a few kilometers at most. And also because many parts of the New York City metro area, certainly New York City and the Bronx, Westchester, bedrock outcrops at the surface. So feeling these events is, certainly that helps as well. Well, having talked about the primary aspects of this presentation, I would like spend some time to revisiting this topic of seismic screening using the cone-penetrometer. As I said, this is something that I've become interested in recent years and talked about at some length in my February 2024 presentation about site characterization at Kennedy Airport using the cone-penetrometer. The concept of seismic screening using cone-penetrometer data was discussed in my YouTube presentation dealing with cone-penetrometer-based site characterization at Kennedy Airport that I posted earlier this year, February 2024. However, given the recent seismic event in New Jersey and the renewed interest in seismic potential in this region, this topic merits some discussion, I think, in this presentation. Seismic screening uses a wide variety of empirical correlations based on basic QC FSU2 data that you obtain from either a piece of cone or seismic piece of cone sounding, as well as shear wave data from a seismic piece of cone sounding, to evaluate the in situ volume change potential of coarse-grained soil under shear, and as a result, the soil's predisposition to liquefaction. Now, there's been quite a bit of research to date that's focused on static or flow liquefaction primarily. And flow liquefaction can have a variety of trigger mechanisms. However, it appears to me that the concept is equally applicable to cyclical liquefaction, where the trigger mechanism is a seismic event. So if you look in the literature, you'll see quite a few papers by Dr. Peter Robertson and others. You see that they talk mainly about static or flow liquefaction applications. Dr. Paul Main has done quite a bit of work in this area recently as well. And I mentioned Doctors Robertson and Main, who I know well professionally because their work figures very prominently in the relationships that I'm going to show you shortly. It's important to point out that seismic screening only indicates a predisposition or potential for seismic liquefaction. You need to do a more detailed site-specific assessment in order to quantify the actual seismic liquefaction potential. I'm not going to get into those sorts of analyses. They're well known, have been covered very well in many other venues. Nevertheless, I think seismic screening is a very, very useful tool whenever you use the cone penetrometer for site characterization, which is hopefully all the time. I think, unfortunately, it is underutilized in many areas, including the New York City metropolitan area, although I do see people using it more than they have in the past, just perhaps not using it to its full potential. And the attraction is that seismic screening, it's very quick and easy in the assessment to make in the scheme of things. You don't need anything more sophisticated than a spreadsheet solution, and it provides you with a first order preliminary screening so that you can devote the resources required to perform the more detailed seismic liquefaction assessments much more efficiently and effectively. So the thinking is that, if you screen sites, that obviously you would begin your more detailed analyses with sites that show some potential for seismic liquefaction. The seismic potential throughout the New York City metropolitan region makes seismic liquefaction a real design concern in areas with coarse-grained soils. Many parts of the New York City region have fairly loose sands, very saturated, very classic scenario for seismic liquefaction. So I think seismic screening using cone penetrometer data has great potential in the New York City metropolitan region. So I'm going to illustrate this for two case histories that have been the subject of earlier YouTube presentations by me. One is Kennedy Airport. This will only be a summary of the much more detailed treatment of the subject I gave in my presentation earlier this year in February 2024. And I'm also going to talk about a site in northeastern New Jersey underlain by Hudson Valley varve clay. I prepared a presentation back in October 2021, and that presentation focused primarily on the stress history and related aspects of the very extensive glacial clustering varve clay deposits at the site. So that earlier presentation was really focused on the varve deposits. I want to revisit that site in New Jersey, and this time focus on seismic screening of the coarse grained strata. However, before I get into this, I want to provide a brief discussion of the primary metric that we currently use for seismic screening for the benefit of those who may not be familiar with the subject, given that it is fairly new in the scheme of things. The heart of this is critical state soil mechanics, and typically you see things plotted as the void ratio versus the log of effective vertical stress in this case. And if you follow cone-penetrometer work, you see that it's been used increasingly in recent years, especially by Dr. Main, as a sound theoretical framework for interpreting cone-penetrometer data. And the heart of critical state soil mechanics is the so-called version compression line, which is normally taken to be a straight line. Of relevance to seismic screening has been the increased focus on the concept of contractive versus dilative behavior. And you see that is based on what is called the critical state line, which is taken to be parallel to the virgin compression line, and again, typically taken to be a straight line. And the critical state line is the dividing line between contractive and dilative behavior, with contractive behavior being a potential for volume reduction and therefore a potential for liquefaction, and dilative behavior defining inherent potential for volume increase under shear and therefore resistance to liquefaction. The heart of this contractive versus dilative behavior is a dimensionless parameter called the state parameter psi, which has a base value of 0 along the critical state line. And as we'll see, this parameter, which is not widely known, it's been slow to be used in many parts of the world, especially here in the US. It really is a superior parameter, as I'll show you, for assessing the consistency of coarse grained soil. You know, normally when we talk about consistency of coarse grained soil, historically we've always talked about relative density. But relative density is actually a very poor metric to use for seismic screening. The reason for the state parameter psi being the primary soil parameter to use for volume change potential of soil is that it has a theoretical framework for quantifying the texture and consistency of coarse grained soil, that something that the traditional soil property of relative density does not provide. And I'll show you why. State parameter is defined as the current void ratio of some soil relative to that which exists at the critical state. So here's a very simple arithmetic expression for calculating the value of psi. So we see that psi has a positive value in the contractive state. All right, contractive state typified very open spacing of soil particles, what we would colloquially call a loose soil. On the other hand, if we have a very relatively tight packing of soil particles, what we call a dense soil, this is typical of the dilative state, and we see that psi has a negative value. So simply by the sign of psi, this provides an objective, quantifiable, right? You can calculate it, way to assess the liquefaction potential. Do I have a tendency to be contractive and therefore liquefaction susceptible, or dilative and therefore resistant to liquefaction? So psi has been chosen to be the primary metric to use for liquefaction screening. And as we'll see, there are some really excellent correlations that have been developed between psi and cone-penetrometer data. So you don't need to do this calculation. There are really high quality correlations between psi and the normal QC-FSU2 data that you measure in cone-penetrometer soundings. Well, in addition to the empirical correlations for quantifying psi, there have been a number of other soil properties and parameters derived from cone-penetrometer data that could be used in a qualitative manner. So again, research by Dr. Robertson and Dr. Main have developed a number of additional parameters that we could use as part of this liquefaction screening. So we're not just putting all of our eggs in one basket with the parameter side. We now have a number of parameters, as we'll see, that we could use. So in summary, the current states of knowledge and practice for cone-penetrometer-based liquefaction screening are based on using a quantitative method based on psi and qualitative methods based on other parameters. So I'm first going to discuss the application of the seismic screening concept to Kennedy Airport in New York City. I've had the opportunity over the last few years to look at dozens of piezo-cone and seismic piezo-cone soundings from Kennedy Airport. So have really developed quite a significant database for the airport. And as I said, I discussed this all in some detail earlier this year. You could look at this presentation if you want additional details. I'm just going to show you a summary of things now. So just as interest, here's the location of Kennedy Airport relative to the April 5th Whitehouse Station, New Jersey seismic events. This is an idealized subsurface profile of the central terminal area at Kennedy Airport. You have a Holocene fill. This is sand that was deposited by hydraulic filling in the 1940s to create the airport. This is underlain by a fairly thin stratum of organic soils, mostly organic clay, a little bit of peat. And then you have a rather substantial coarse-grained stratum of Pleistocene age that is known as the upper glacial aquifer. And this is typically as deep as piezo-cone and seismic piezo-cone soundings extend. Most borings only extend here as well. There's been research in recent years. We now know that the upper glacial aquifer can be broken into at least two distinct formations, the Merrick and the Belmore. This is just the normalized soil behavior types using the most recent 7-zone version proposed by Robertson. And these are the ones we want to look at. S meaning predominantly coarse grain or sandy soils, D for dilative, C for contractive. And we see that most of the soils for the ones that I've colored in are the coarse grain strata we want to focus on. Most of these data points fall into the dilative range. These green dots, these are all for the organic clay, so we're not going to consider those. But we do see that there are some data points in the contractive range. All right? So these are the ones that are concerned to us. So I'm first going to look at the broadest seismic screening assessment based on using QCFS and U2 data from either a piezo-cone or seismic piezo-cone. And this looks very confusing at first, but what I'm showing you here is a function of depth of historically, when we think of the consistency of coarse-grained soil, we focus on relative density. And of course, nowadays we can get correlations between cone-penetrometer data and relative density. And these are the end results for one typical seismic piezo-cone sounding. If you want details about specific correlations, etc., you could view my earlier presentations. Well, as I said, the problem with relative density is we don't know what relative density might be a threshold between contractive and dilative. And that's where quantitatively the state parameter comes in. Now, theoretically, 0 is the dividing line between contractive and dilative. However, research has shown that actually a value of minus 0.05 is better to use as the threshold between contractive and dilative. And if we look here, we see that, again, for the coarse-grained strata, it appears that there are some zones where we stray below the minus 0.05 threshold. Well, as I said, there are a number of qualitative assessments that have been developed. For example, we could use Robertson's 7-zone normalized soil behavior type index, which explicitly has contractive versus dilative zones. We could use normalized tip resistance, research by Paul Main and his colleagues have shown that the clean sand equivalent normalized tip resistance, a value of 70, is an effective dividing line between contractive and dilative. With soil unit weight, again, empirically we found that a ratio of total unit weight to unit weight of water of 1.8 is a qualitative dividing line between contractive and dilative behavior. And finally, yield stress ratio based on critical state assessments. A yield stress ratio at the critical state line typically had the brown data points here, typically has a value of about 3. If the actual yield stress ratio that we estimate based on cone data is below that, we might have contractive behavior. I will tell you that certainly in my experience with Kennedy Airport, this yield stress ratio I have found is probably the least reliable of all of these. That's not to say we shouldn't use it, but I'm just saying that for this specific extensive research I've done at Kennedy Airport in recent years, I find this particular metric to be the least reliable compared to these other ones. So just look at one typical example. Here's a case where we have a zone that based on state parameter, we would flag this if we were doing a seismic liquefaction screening. We would flag this as being potentially problematic. Okay, it falls in the contractive zone less than minus 0.05. Notice the consistency across these other metrics. It would plot in contractive zone using the soil behavior, normalized soil behavior type index. It would fall below this magical value, threshold value of 70 using normalized tip resistance. It would fall below 1.8 using the soil unit weight ratio, and clearly it falls below the critical state yield stress line, yield stress line using yield stress ratio. So what I'm pointing out to you here is where we develop some confidence that we've identified a potentially contractive and liquefiable zone is where we have a consistency between several metrics as we do here. Well, before leaving this, let's look at relative density out of curiosity. As I said, I have looked at dozens and dozens of piezo-cone and seismic piezo-cone soundings taken at Kennedy Airport in recent years. And one of the things I found is that I think it might be possible, in the same way we've developed empirical thresholds here, 70 and 1.8, I think it might be possible, at least I've tentatively suggested, that we might be able to do this for relative density. And in the case of Kennedy Airport, I found that a relative density of 50%, which is in the middle of the medium dense range, appears that it might be an empirical threshold between contractive and dilative behavior. And certainly we see that here. Notice we get good correlation with psi here, a couple of other data points down here, a little bit here at the very top of the upper glacial aquifer. So I think there's some merit in doing some additional research to see if we can use relative density, at least an empirical way, to as part of the seismic screening process. Well, as I said earlier, when we do a seismic piezo-cone, we can make an additional seismic screening assessment based on the measured shear wave velocity data. And here I plotted the measured shear wave velocity. In this particular seismic piezo-cone sounding, the readings were taken every 1.5 meters, so about every 5 feet. And I compare this with psi, and again, the basic data were taken every 50 millimeters or 2 inches. So we get many more data points here. One of the things I found in literature is very often you'll see a shear wave velocity of, again, this is empirical, of 200 meters per second, being a threshold between contractive and dilative behavior. And in this case, we would see this would suggest that we might have potential liquefaction within this zone. And we see there's actually pretty good correlation. It's not perfect, but we see that, again, considering that these data were taken every 50 millimeters and these were taken every 1500 millimeters, we see that we have several places here where the state parameter psi suggests that we might have liquefaction issues. And overall, I think there's pretty good correlation here as well. So again, the idea with seismic screening is you don't put all your eggs in one basket. Yes, you always look at the state parameter psi, but you also look at some of these empirical correlations with normalized tip resistance, weight ratio, shear wave velocity when you have those data. And this must be measured shear wave velocity, all right, not calculated empirically. The idea is to look at several of these metrics side by side, and where you start to see consistency of suggestions of a contractive zone, this is an area that you might flag as, gee, maybe I should take a closer look at this and do a more refined analysis to see if I have a liquefaction issue here. So next I want to discuss the application of the seismic screening concept to a site in northeastern New Jersey that lies within the aforementioned Newark Basin and is underlain by sediments from one of the several glacial lakes that existed during the Pleistocene epoch within what is now the New York City metropolitan region. The signature geotechnical feature at this particular site is a relatively thick deposit of glaciolacustran varve deposits that I refer to regionally as the Hudson Valley Varve Clay, or HVVC. Very similar in concept to the Connecticut Valley Varve Clay, CVVC, that you've seen talked about in the literature for many years. And these varve deposits are primarily fine-grained in nature, and they're overlain by a relatively thick stratum of Pleistocene outwash sand. as well as Holocene fill that is predominantly coarse-grained in texture. Now, I did an extensive cone-penetrometer based site characterization presentation for the site back in 2021. So if you want additional details about the site, I would refer you to that earlier presentation. So here's the location of the site relative to the April 5th main shock and the subsequent aftershocks we've been talking about. And just out of curiosity, this green triangle you see here, that's the location of Lamont Doherty Earth Observatory, and specifically the PAL seismograph station that is part of the Lamont Doherty seismograph network. So here's an idealized soil profile at the HVVC site. We have a Holocene fill as predominantly sand. This site used to be in the floodplain of an adjacent freshwater river. And then this is underlain by about 10 meters of Pleistocene outwash sand. And then you see a very extensive deposit of varve clays with some significant variation in consistency and stiffness. All the cone soundings done for this project terminated here, about 40 meters below the ground surface. Then there's a till stratum, and finally the shale bedrock that is one of the characteristics, sedimentary rocks in the Newark Basin I mentioned earlier. And again, if we look at normalized soil behavior type using Robertson's latest 7-zone version, we really want to focus our attention on the coarse-grained soils. And we see that most of them plot in the dilative range, but we do have a few data points in the contractive range that we would be concerned about. All of these other data points are for the varve deposits. So this is similar to what I showed you previously for the Kennedy Airport site. And again, we're just looking at the coarse-grained strata, the Holocene fill, and the Pleistocene outwash. And if we look at our state parameter, we see that in general, most of the values are well above the minus 0.05 threshold, plotting very nicely in the dilative range. Although if we look, we see that there is a significant part of the Holocene fill where we have values in the contractive range that we would be concerned about. And again, if we look across some of these other metrics, we would see consistency here in soil description, values less than 70 indicating contractive, these values indicating contractive, these indicating contractive. And if we look at relative density, again, using that 50% criteria that I've tentatively suggested based on my research at Kennedy Airport, again, we would see actually it would correlate pretty well. We see that we have an extensive zone here where we likely have contractive behavior. So again, you want to look at not just the state parameter, we'll look at some of these other parameters as well. And where you have consistent suggestions of contractive behavior, this would flag a region that in practice you would want to pay more attention to with more refined analyses. And again, this is really the whole logic behind seismic screening. It's not the final answer. It's just a preliminary initial answer. It's to point you in the right direction of what strata or what portions of strata really merit further detailed analyses for their seismic liquefaction potential. And if we look at shear wave velocities for the one seismic piece of cone that was done at this site, here we see the shear wave velocities suggest you might have some issues going down into the Pleistocene sand that do not correlate well with state parameter or other things. Again, these correlations, you're never going to get 100% perfect consonance between all the different metrics. The idea is to look at several metrics and to focus your attention on zones where you have some consistent results. And again, this would be, we see that a good portion of the Holocene fill, which was not placed in any controlled fashion, is potentially problematic. That comes as no surprise. Well, that brings us towards the end of this presentation. I'd like to offer some closing comments. These are really just my personal opinions as to what do we make of everything, and where might we be going in the future. I think it's safe to say that the Whitehouse Station, New Jersey earthquake of April 5th, 2024 was a reminder to geologists, civil engineers, and the public at large that seismogenic intraplate brittle faults are found extensively throughout the New York City metropolitan region. So we certainly have a setting in this region where we have brittle faults that are potential sources of seismic events. Geological research documenting the seismic history of the New York City metropolitan region, at least going back to the 17th century, has shown that seismic events of relatively significant magnitude, while infrequent, can and do occur, and therefore they justify the need for seismic design of constructive facilities, probably more than we do at present, to be honest. And certainly better seismic preparedness than presently exists for the public at large within the region. I think we should note that the magnitude of the April 5th event in New Jersey was remarkably large, not only for the New York region as a whole, but certainly for the Ramapo Fault Zone specifically. Right, it bears repetition that if we look at a very extensive, going back to the 1600s, very extensive assessment of faults that are epicentered along the Ramapo Fault Zone, and to a more limited degree here going back to 1970, the event of April 5th, 2024 certainly stands out for its significant magnitude. So suggesting that we might pay a little bit more attention to the Ramapo Fault Zone than we have historically. Historically, a lot of the focus has been on some of these strike-slip faults we find in Manhattan, the Bronx, and in Westchester County. However, the Ramapo Fault merits some consideration as well. And one of the things to point out, and I perhaps should have done this earlier, is that if we look at the Ramapo Fault as it goes through Pennsylvania, through the entirety of northern New Jersey, into lower part of New York State, it does cross the Hudson River here in the vicinity of Peekskill, New York. And rather interestingly, it is known to go under the site of what is called the Indian Point Power Plant. All right, there are three nuclear power plants in one location here near Peekskill, New York, on the east bank of the Hudson River. These are some of the earliest nuclear power plants built in the United States for commercial purposes, dating back to the 1960s. They are no longer in service, but they certainly still exist, and there still is nuclear fuel there. So it's been long known that the Ramapo Fault does go underneath the plants, but in view of this recent history of faulting along the Ramapo Fault Zone, maybe time to take a closer look at what's happening under Indian Point as well. I think the recorded number of aftershocks, about 50, is also remarkable. Although modern seismograph measurements for earthquakes in the New York City area are not all that common, certainly there were several aftershocks measured for the Ardsley earthquake in 1985. Again, that was magnitude 4.0. But to me, the number of aftershocks here is almost 50 is quite remarkable. And I think that, if nothing else, should hopefully lead to new geological investigations and research of the Ramapo Fault, because as Dowers and Sieber noted in 1991, in regions such as eastern North America, where surface rupture data for historic earthquakes are lacking, again, as I mentioned earlier, very often we don't see fault traces, even where bedrock is exposed. Aftershock sequences are particularly important in delineating the orientation, size, and depth of ruptures. And if you look at their paper from 1991, you see that they talked about, in particular, I think it was a magnitude 5 or so earthquake upstate New York in the Adirondack Mountains, where there were several aftershocks. And those aftershocks were studied in detail to really home in on the orientation and depth of the fault zone that was originating these earthquakes. All right, so let's keep in mind that if we look at the foreshock, main shock, and all the aftershocks that occurred in March and April of 2024, we're looking at more than 50 events total. And I would like to believe that using modern day records and assessment tools, that seismologists could really study this to really home in on what is exactly is happening along this section of the Ramapo Fault Zone. I'd like to close with one final thought. It should be noted that there are other geological investigative tools, such as paleoseismology, that can be used to estimate magnitudes and dates of historical earthquakes based on relict features from seismic liquefaction and tsunamis. I mention this because paleoseismology has been used to very great advantage in coastal New England. And if you're not familiar with the seismic history of New England, it has a seismic history that's reasonably similar to that of the New York City metropolitan region. And this is from a undated publication by Dr. Tish Tuttle, who's done a very, very nice research on paleoseismology, not just in New England, but in other parts of the U.S., New Madrid Fault down in South Carolina. Again, we're looking at New England, the black lines being known brittle faults. And again, here we see symbols for different earthquake magnitudes. Of course, New York City would be here. You see a little bit of Long Island. New York City region would be down here off the map. When people talk about New England earthquakes, everybody talks about the 1755 event called the Cape Ann event, that depending on the particular magnitude scale you use, probably at a magnitude of about 6. So certainly the high end of what we think can happen in the New York City area. But there have been some smaller events as well. In particular, we see one here near Newburyport, Massachusetts, that is very similar magnitudes that we see down here in the New York City area. Well, I flagged this event in Newburyport because, as I discussed in my first YouTube presentation on Kennedy Airport back in 2020, I talked about these paleoseismological studies in New England in some detail. They produce some very interesting evidence that historical earthquakes epicentered along the New England coast may have produced not only seismic liquefaction, but also tsunamis that impacted the coastal areas. You don't very often hear about tsunami and east coast of the United States in the same paragraph, no less the same sentence. Again, we look at this work that Dr. Tuttle did in the Newburyport area, where Dr. Tuttle and her colleagues found evidence of liquefaction as well as possible tsunamis. And by the way, it is interesting to look at the fault plane solution that we're looking at here. This is also indicative of a reverse or thrust type of fault. So it is interesting to see that the type of fault plane mechanism of a reverse or thrust fault is really almost identical to the type of motion that we associate with the Ramapo Fault. These are some of the details that they found in the Newburyport area. This sand dike, this is something that in paleoseismological studies, this is characteristic of seismic liquefaction. All right, this is an event where sand came up and vented to the ground surface. You see the different colored sand compared to the native sand on either side of it. So this sand dike, based on dating of adjacent peak, seems to have been from about 2,700 years or so before present. I think even more interesting that they found some killed trees that are reminiscent of confirmed tsunami deposits in the Pacific Northwest. So these sorts of trees that were basically drowned out are suggestive of a tsunami event. And the dating of this possible tsunami deposit is about 2,000 years before present, and may actually have occurred around the same time as this liquefaction. So there are many sites in the New York City metropolitan area, I think, where both coastal and inland, that could be investigated for paleoseismological evidence of seismic liquefaction. And I think for coastal sites, you could also look for tsunami evidence as well. And I base this on the fact that certainly these conditions have been found in New England. New England has been subjected to earthquakes that are very similar, broadly similar in nature, both in terms of magnitude and thrust faulting, reverse faulting, as we see along the Ramapo Fault in particular in the New York City area. So I think there's enough similarities between New England and the New York City metropolitan area that we should really be devoting resources to doing some of these paleoseismological studies. And the reason for doing that is if these conditions are found, they could be a really very important contribution to the regional catalog of seismic event magnitudes and dates of occurrence. I mean, right now our catalog is constrained by the human record, the written record, and that really limits us as to how far back in time we could go. So instead of being constrained by human recorded history, by looking at seismic evidence based on physical things such as liquefaction, it may be possible to extend this record in terms of magnitude and time much farther back in time than has been possible to date. And with that, I want to bring this presentation to a close. I want to thank you for your interest and attention. I think, to me, this seismic events in New Jersey in early April 2024, really very thought-provoking. It's a reminder of what we know from the past has happened, and also I think should be a wake-up call of we should probably be doing a few more things more than we have up to this point in time.